In this video, we are going to discuss test of hypothesis in small samples. Any sample of size less than 30 is called a small sample. So whenever we have a sample of size less than 30, then the theory of large samples will not work, because in that case the sampling distribution of the sample statistic will not follow normal distribution. That's why we have to change the test and we have to use students' t distribution for testing the hypothesis. So let's discuss what is test of hypothesis in small samples. So first we discuss the test of significance of difference between sample mean and the population mean. So suppose x bar be the mean of a small sample of size n and a standard deviation s drawn from a normal population with mean mu. So here also we assume that the population from which the sample has been drawn is normal. Therefore, from the theory of estimation, expectation of x bar equal to mu and variance of x bar equal to s square upon n minus 1. Therefore, the test statistic is t equal to x bar minus expectation of x bar divided by standard error of x bar. This standard error of x bar is nothing but the standard deviation of this mean. So standard deviation of this mean will be under root of s square upon n minus 1. So which comes out as s upon root n minus 1. So this is the test statistic for testing whether the difference between the sample mean and the population mean is significant or not. Where this s is obtained using this formula. So here in case of small samples, we use this formula for the standard deviation. Instead of dividing by n, we divide by n minus 1. So in case of a small sample theory, this is the formula for the standard deviation of the sample observations. And the degree of freedom here is nu equal to n minus 1, because we have been using this x bar in calculating s. Therefore, degree of freedom will be n minus 1. So after calculating the value of t from here, we compare this value of t with the critical value of t at level of significance alpha at degree of freedom nu. And if we find that this value is greater than this critical value, then we reject the null hypothesis and accept the alternative hypothesis. And the 95% confidence interval is given by x bar minus t nu alpha standard error of x bar to x bar plus t nu alpha standard error of x bar. So we can find either 95% confidence interval or 98% confidence interval using this formula. Here t nu alpha will change in case of 98% confidence interval. So consider an example. A random sample of 8 envelopes is taken from the letter box of a post office and their weights in grams are found to be 12.2, 11.9, 12.5 up to 12.4. Can it be concluded that the mean weight of all the envelopes in the letter box is 11.7 grams? If not, also find the 98% confidence limits for the mean weight of the envelopes in the letter box. So in this example, we have been given 8 envelopes. That means we have a small sample. And the weights of these 8 envelopes have been given as 12.2, 11.9 up to 12.4 grams. So we have to tell whether the average weights of all the envelopes in the letter box is 11.7 grams. For this purpose, we note down all the information. So n equal to 8, that means sample size. Mean of all the 8 envelopes is 12.1. Mu, mean of all the letters in the letter box, 11.7. This is assumed mean. This is claimed mean. Then we set h0 as x bar equal to mu. That means the mean weight of the letters in the letter box is 11.7 grams. That means there is no difference between the mean weight obtained from the sample and the mean weight of all the letters in the letter box. We set h1 as x bar not equal to mu. That means mean weight of the letters in the letter box is not 11.7 grams. In other words, we can say there is a significant difference between the mean weights of letters in the letter box and the mean weight of the letters obtained from the sample. Here degree of freedom is 8 minus 1 equal to 7. Alpha equal to 2% level of significance, because 98% confidence interval has been given. And here we have to use two-tailed test. So we note down the critical value of t at 7 degrees of freedom at level of significance 2%, which is 2.998. That means this 2% area total on both the sides. So this is 1% area, this is 1% area. So minus 2.998 to 2.998. We have total 2% area. So 1% area on left, 1% area on right will be the critical region. And in between these two values, we have acceptance region. So we have to see whether our calculated value falls in this acceptance region or in critical region. Now here we have to calculate S, which is standard deviation. So for this we calculate S square, which is 1 by n minus 1 xi minus x bar whole square. So here we divide by n minus 1 instead of n. So if we find s square, then we find that s square is 0.11. Therefore, the value of the test statistic t is x bar minus mu upon standard error of x bar. So which comes out as 3.19. Now if we compare this value 3.19 with the critical value, then we find that this value 3.19 falls in the region of rejection. That means it falls here, while the critical value is 2.998. So acceptance region is from minus 2.998 to 2.998, and this value falls outside of this acceptance region. So H0 is rejected. That means the mean weight of the letters in the letter box is not 11.7 grams. Then what it should be? If it is not 11.7 gram, then what it should be? So for this purpose, we find 98% confidence limits using the formula. So using this formula, if we find the interval, then we find that the mean weight of the letters in the letter box is 11.74 to 12.46. So mean weight of the letters in the letter box must be from 11.74 to 12.46 grams. This is the confidence interval. Take another example. A sample of 9 shafts is inspected from a production line. The following measurements are the diameters in millimeters of shafts. If the production line meets the specification laid by ISI, estimate the 95% and 98% confidence intervals within which the true diameter of the shaft lies. So here n is 9, sample size is 9, degree of freedom is 9 minus 1 equal to 8, diameter is 45.017. So this is mean diameter of 9 shafts, and variance of these 9 shafts using this formula, we find that variance is 0.00003. That means almost 0. So standard error is s upon under root n minus 1, which is 0.0019. From the table, at 8 degrees of freedom, at 0.05 level of significance, the value is 2.31, and critical value of t at 2% level of significance at 8 degrees of freedom is 2.90. So using the formula, 95% confidence interval is this. 98% confidence interval using the same formula with this 2.90 value, we find that this is the 98% confidence interval. Here in this interval, we are ready to reject 5% of the shafts on the basis of their diameters if their diameter lies outside of this interval. And here we are ready to reject 2% of the shafts if their diameters fall outside of this interval. Now discuss test of significance of difference between means of two independent small samples. So suppose x1 bar and x2 bar be the means of two small samples of sizes n1 and n2 with standard deviations s1 and s2 respectively, drawn from a normal population with mean mu. So here we take either same population or two different populations. So from the theory of estimation, expectation of x1 bar minus x2 bar equal to 0 in case we take the same population or two different populations with same mean, or in case if we take two different populations with two different means, then this will be mu1 minus mu2. So there is no problem. It may be 0 or mu1 minus mu2 depending on we are taking same population or two different populations with mean mu1 and mu2 respectively. Variance of x1 bar minus x2 bar is equal to this. This is from theory of estimation. Therefore, the test statistic is x1 bar minus x2 bar divided by standard error of x1 bar minus x2 bar. So this is at degree of freedom n1 plus n2 minus 2. If n1 not equal to n2, then total degrees of freedom will be n1 plus n2 minus 2, because total n1 minus 1 degrees of freedom is when we calculate s1 square, and another n2 minus 1 degrees of freedom will be there if we calculate s2 square. So total degrees of freedom will be n1 minus 1 plus n2 minus 1. So total is n1 plus n2 minus 2. In case both the samples are of same size, then this will be the formula. So this formula reduces to this in case we have n1 equal to n2 equal to n. So let's take an example. Two independent groups of 10 children were tested to find how many digits they could repeat from memory after hearing. The results are as follows. Group A and Group B. So these are the number of digits repeated by them after hearing. Is the difference between the mean scores of two groups significant at level of significance 1%? This we have to check. So here n1 equal to n2 equal to 10. So both the samples are equal. The mean score of group A is 6.2 and the mean score of the group B is 7.3. So we have to test whether this difference between 6.2 and 7.3 is significant or not. So H0 we set as x1 bar equal to x2 bar. That means the difference between the mean scores of two groups is not significant. at level of significance 1%. That means mean scores are the same. And in H1 we assume that mean scores are different. So here we are not interested which one is greater or which one is smaller, but we are interested in only they are not equal. Degrees of freedom will be 2n minus 2. That means 20 minus 2, which is 18. And critical value of t at 18 degrees of freedom and 1% level of significance is 2.8784. That means total 1% area on both the sides. So this is the critical region. So this is 0.5% area, this is 0.5% area, and the critical values are minus 2.878 to 2.878. So this is the acceptance region and this is the critical region. Now S1 square if we calculate, so S1 square comes out as 6.044, S2 square comes out as 7.7100. Therefore test statistic is minus 0.8911. So this is minus 2.8784. So this value is somewhere here. So H0 is accepted. That means the difference between the mean scores of two groups is not significant. They are same. Take another example. To compare two kinds of bumper guards, with each kind were mounted on a certain make of compact car. Then each car was run into a concrete wall at 5 miles per hour, and the following are the cost of the repairs in dollars: bumper guard 1 and bumper guard 2. So two samples have been taken. Test at alpha equal to 0.05, that means 5% level of significance, whether the cost of repairs for the bumper guard 1 is less than that of bumper guard 2. So again here we note down sample size 1 is 6, sample size 2 is 7. Average cost of repairs is $145.5 and average cost of repairs for bumper guard 2 is $152.86. So suppose H0 x bar equal to y bar, that means the cost of repairs for bumper guard 1 and that of bumper guard 2 are the same, and H1 is the cost of repairs for bumper guard 1 is less than that of the bumper guard 2. Degree of freedom is total 6 plus 7 minus 2, which is 13 minus 2, which is 11. And the critical value of t at 11 degrees of freedom at 5% level of significance for left tail test is minus 1.796. So this is the critical value. So this is minus 1.796. So total 5% area on left hand side at 11 degrees of freedom. Now S1 square if we calculate, then S1 square comes out as 29.1. Similarly, S2 square comes out as 39.48. So what is T? T is x bar minus y bar upon this standard error of x bar minus y bar for n1 not equal to n2. So if we calculate this, we find that T equal to minus 2.0661. So if we compare this value with the critical value, we find that this value falls outside of this region. So minus 1.796 is the critical value on left. Minus 2.0661 is falling outside of this acceptance region. So it is in the critical region. Therefore H0 is rejected. The cost of repairs for bumper guard 1 is less than that of bumper guard 2. Now look at another example. A research team wants to investigate the usefulness of relaxation training for reducing levels of anxiety in individuals experiencing stress. They identify 15 people at random from a group of 100 who have high stress jobs. The 15 people are then divided into two groups. One group of 7 called control group receives no training. The second group of 8 called relaxation group receives a relaxation training. The subjects in each groups are then given an anxiety test. The scores are given in the following table, where high scores are indicating greater anxiety. So there are two groups, control group and relaxation group, scoring these numbers. Test whether the relaxation training has reduced the anxiety at level of significance 1%. So here the size of first group is 7, size of second group is 8, mean score of control group is 35.28 and mean score of relaxation group is 30.62. So here we see that the score is different. So suppose H0, the relaxation training has not reduced the anxiety. That means there is no difference between the two scores. X bar greater than y bar means the relaxation training has reduced the anxiety. Here degrees of freedom is 8 plus 7 minus 2, which is 13, and critical value of T at 13 degrees of freedom at 1% level of significance is 2.650, which is on right. So we have to use the right tail test. So this is on right, 1% critical region is on right side, and this value is 2.650. Then S1 square if we compute is 9.9048, S2 square if we compute, this is 12.27. Therefore, the value of t is 2.51. So computed value of t is 2.51, and if we compare it with the critical value, we find that this falls in the acceptance region. This is the acceptance region, 2.650. This is the critical region. So this value is falling somewhere here. So H0 is accepted. Therefore, the relaxation training has not reduced the anxiety because the mean scores of control group and the relaxation groups are the same. Now we discuss test of significance of difference between means of two dependent samples drawn from the same normal population. Let two samples of size n be drawn from the let two samples each of size n be drawn from a normal population. Let the pairs of values of samples are correlated. Then we set H0 as d bar equal to 0. Here d bar means x bar minus y bar. Because here we have to take pairs of the values. We cannot shuffle them. We cannot put them in arbitrary order. We have to pair them. So here test statistic is d bar upon s upon under root n minus 1. So instead of taking x bar minus y bar, we take d bar, where this d bar equal to x bar minus y bar, and s is the standard deviation of d. D is the difference between the values xi minus yi. So this is the standard deviation this time. So look at an example. The following data relate to the marks obtained by 11 students in two tests. One held at the beginning of a year and the other at the end of the year after intensive coaching. Do the data indicate that the students have benefited by coaching? Test at level of significance 10%. So here the same student has been given two tests, one before coaching and one after coaching. So therefore we have to pair the observations. Here 19 and 17 is a pair. Here 23 and 24 is a pair, and so on. You cannot shuffle them or write in any order because you have to pair them. So here x bar equal to 19.54. That means the mean score of the students before the coaching and mean score of the students after the coaching, 20.54. Total number of observations 11 or sample size 11. Difference between the means is -1, and difference between the scores of each student 19 minus 17 2, 23 minus 24 -1, 16 minus 20 -4, and so on. Therefore variance is 1 upon n minus 1 summation di minus d bar whole square. This is the variance of the difference. So variance comes out as 5.8. Standard deviation is square root of 5.8, which is 2.408. So suppose H0 d bar equal to 0, that means that the students are not benefited by the coaching. That means the mean scores before and after the coaching are the same. H1 d bar less than 0, that means the students are benefited by the coaching. That means the mean score before the coaching is less than the mean score after the coaching. So we have to use left tail test. Here degrees of freedom is 11 minus 1, which is 10, and critical value of t at 10 degrees of freedom at a level of significance 10% is -1.372 from the table. So if we calculate, we find that t equal to -1.313. So if we compare this t with the critical value, we find that this value -1.313 falls in the acceptance region. Therefore H0 is accepted. That means the students are not benefited by the coaching. The mean scores before and after coaching are the same. So this was testing of hypothesis in small samples. I hope you understood what I have told you. Thank you very much.